Okay, we go to the next lecture, and this time we will be talking about air jet texturing jets. Some fundamental aspects of the design of jets is what we would like to discuss in this lecture. Let us see what we have learnt. Till now, we have learnt about various parameters that affect the properties of air jet textured yarns. In addition, we have also learnt the role of wetting, which was that it always in all cases reduces instability, and that was because the tension at the exit of the yarn is always high because of wetting. So, wetting increases the tension in the yarn at the exit and therefore, decreases the instability. Today, we shall focus on the design of jets, how they change with time and why. Air jets. Remember, we said that although the principle of air jet texturing was known pretty early, you are not able to get commercial machines because the productivity was low, the speeds of the texturing machines were very, very low, because otherwise the entanglements would not be good, yarn would have higher instability, which obviously is a bad property, bad thing to happen. So, there was one concept which people wanted to try. Can we do a bit of a pre-twisting instead of just putting the filament yarns, untwisted filament yarns for air jet texturing? Can we do some pre-twist and then texturize the yarn? And this is what people actually checked it out and found that during the air jet texturing process, the pre-twist gets opened, gets untwisted, entanglements are facilitated, and as the yarn would exit, it was hoped that the twist will flow back and the entanglements become tighter, and therefore, possibly the yarn instability, textured yarn instability would be low. One of the interesting jets was called the Merlin jet. It was designed in Czech Republic, earlier called Czechoslovakia. Now, what was there is this yarn, there is a jet, the yarn which is a pre-twisted yarn, yarn is fed, of course, overfed, but the air is going through a chamber from outer chamber to the inner chamber, from where, if you look at the cross section, the yarn may be coming out, for example. The air is entering from the sides, and through this chamber it goes from here to there, there to here. And also, if you see from this, there was a angle which is towards the exit. So, the air is going to be pushed out generally, but because of this thing that it is entering the innermost chamber in three directions, it would push the yarn in a manner that it starts rotating. So, a bit of a twist or untwist, we are interested in untwist. So, the directions could be such that this actually behaves like as if it is untwisted, and the because the overfeed you would have loops formation and entanglement and everything else, and as it comes out, the effect of this swirling motion may be reduced or finished, and so the twist flows back in some position, and so yarn becomes still tighter. So, you start with a pre-twisted yarn, you end up with a pre-twisted yarn, post-twisted yarn, right. Start with a pre-twisted yarn, end up with a post-twisted yarn. In between, the twist has been opened, the yarn filaments become loose, they do make loops, entanglements, and the twist flows back as it exits, and so tighter filaments are there, tighter loops will, tighter entanglements will be there. So, less instability. So, it was true and seen by many workers that pre-twist helps. So, it was one of the solutions, but one must remember, every time you do a twisting, a real twist, because the pre-twisted yarn means there is a real twist in the yarn, and if that real twist is there, then it becomes a batch process. So, batch process means first you do twisting, then make packages, then take the packages and try to do the texturizing. So, a batch process, a costly process. So, this jet may actually be doing this detwisting in a way by swirling, that is what the jet can do. So, shall we say that the Merlin was using a pre-twisted yarn? The mechanism was something like a false twist insertion or false untwist twisting, and result was instability was reduced. But as we mentioned again that it will be a batch process, twisting will be a batch process. So, costly. So, you needed something else. That means, you wanted jets to use untwisted yarn and exactly produce the quality that is desired. So, various series of jets were introduced by DuPont, they were known as Tusslin jets. So, you can see we are talking at the moment of something like a jet which was type 9. So, previously other versions obviously were introduced in the market and the learning was going on. So, one of the jets which is the type 9 Tusslin became a commercially successful jet. What it also meant that good quality yarn at relatively higher speeds, in which there was a feed tube, which is this feed tube is at an angle. You can see this at an angle. The yarn is going to be fed through this tube, and therefore, this is also entering the jet at some angle. The compressed air is coming directly in a straight direction, but it would interact the feed tube and the yarn coming out at some place here. So, there is some kind of a cavity here. The feed tube can go up or down. This you can see is the converging point, and because it is convergent, the velocity will be high, the pressures at this point will be obviously different. So, high pressure because area is less. So, there is some additional turbulence will be there, and then another attachment which is, so this different obviously at different parts. So, the feed tube can go come and out, this particular exit of the jet can also be moved in one direction or the other based on what the requirement is, and the textured yarn would come out entangled from this side. So, interestingly, this was not obviously using any twist, this one advantage. The turbulence was being created because the movement of the yarn direction and the direction of the air were different, and so they were entangling at some point, and so a lot of things were done. Now, a lot of patents are available. Obviously, what should be the angle at which the yarn must be fed. So, ultimately various angles have been tried, and finally, it appears to be close to 45 degrees at which it is entering. So, yarn is being pushed, the yarn is being sucked by the air, which is at a different angle, and the yarn by itself is coming in a straight way, and obviously it can go out only, there is no other way. This had therefore some salient features. Air is moving straight in the direction of the exit of the jet. Okay. The yarn through a feed tube enters at a different angle. Now, this angle can be changed, but the tube can also come in or go out. A cavity is there for creating turbulence. So, the yarn, the air has to go and take a curve path, increase turbulence and go. Of course, there is going to be convergence, and finally, it appears there is a divergence also, and diverging exit and convergence initially. So, that the pressure increases in some way, and velocity particularly becomes high. So, you cross the Reynolds number. The next version, which we call as Tusslin 10 or Tusslin, shall we say, type 10 jet, some order has been changed here. What has been changed? Now, the air is coming from a different direction now, and the yarn is entering in this direction and exiting this way. So, this is as the nozzle direction is there, in the same direction the yarn is moving, while the air is coming from almost right angles. It comes and gets into the chamber all across, then goes like this, and somewhere here they meet, the yarn and the air, they meet. Interestingly, you can see the exit of jet is not diverging here, while there is a convergence as the feed tube enters, the air all along comes and then moves. Then what do we do with that? So, here somehow it was felt that there was no need of diverging exit. So, yarn gets sucked from the front end, the feed tube can also go in and out, the exit element can also go in and out, but from the type 9 this was a major change. So, what should be the angle of the feed tube, etc., they were no more important. So, for this type 10 jet, the salient features which changed from type 9, the feed tube for yarn was aligned in the direction of the jet exit. That is one change. The compressed air enters at right angles in the jet chamber. So, there is this jet chamber. It distributes uniformly, right? It distributes uniformly all along the feed tube, but converges. So, the overall volume through which it is going to enter is being reduced, and so again velocity will increase, turbulence will increase, and so drag will increase, and hopefully all the kind of entanglements etc. would also increase. And they found that this was efficient enough. So, converging to generate more velocity, in a way more mass flow within the same time period, and at the tip of the feed tube there is interaction with the yarn. So, everything that is supposed to happen would happen here, but there was no diverging exit, it was simple straight exit. Okay. So, the previous research was almost thrown out. Then the Tusslin type 11, you see some difference here. The air is coming from here, obviously compressed air. No, I am sorry, the yarn like type 10 is coming the same direction, the air is at right angles entering. They somehow realized that diverging jet is a good idea. So, diverging jet exit they found was a good idea. So, they brought it back again. However, it was still converging. So, the air enters in a chamber and then gets converged and then goes out. But interestingly, they put another disc over the feed tube. The feed tube was going inside the disc, there was a hole, but the air first was collecting in a chamber like this, but was not going symmetrically and meeting the yarn. So, the asymmetry was created. How? This disc would only allow the air to pass through only one hole at one side, right. So, there is a hole here. So, asymmetry was created. Why? Because they found asymmetry is better for creating more turbulence rather than symmetry. In the type 10, the air was symmetrically entering all across the feed tube and interacting with the filament at the end of the tube. Now, the whole chamber has been divided into two parts, where the air first collects, the first part, and then it enters, can't enter from, let us say, this side, it is closed, it enters only from, let us say, this side. So, it is a disc, and disc has a hole somewhere. The air enters through this hole, feed tube is fixed tightly here. So, around the feed tube, now you see the air is going to be entering from a small hole or orifice in the disc and going to be asymmetrically entering. They consider this will give higher turbulence. Now, remember, the speed started increasing of the air jet texturing machine. They could get into 500 meters per minute. Earlier, remember, we were talking about 30 meters, 50 meters per minute kind of environment in the beginning. Now, you are getting into 500. So, it is basically texturing, air jet texturing is now became quite competitive with these kinds of jets coming in as the speeds increase. So, production high, cost is less. At the same time, entanglements are good, that means instability is low. That is what basically was required to be done. So, some salient features of type 11 jets. So, become converging diverging. Converging, so that velocity increases, diverging, again they gave back as to this will be more important. We will talk about this diverging and effect of this. Asymmetric entry of the air around the feed tube to create more turbulence. The feed tube is similarly aligned as the type 10, all right. So, difference only is asymmetric entry and of course, converging diverging type of a jet. So, why this all changes were made? What happens exactly in the jet and where does it happen? This understanding can then explain what changes which have been done before, why such changes have been done and what more changes could be done. What do we want from the air jet texturing jet? We understood earlier that three things need to be done. One is the opening of the filament. So, bundle is coming which is to be opened, because each filament must make loops individually, not as a bundle. If they make the loops as a bundle, it will open also very easily. Then you require entanglement. These are the three things which have been done. In which part of the jet all these things happen? Let us say roughly this is some kind of a jet, simple. The air is entering from this side, the yarn is entering from here, let us say, and then we will get a textured yarn at the end. So, all these three things, that is opening, loop formation and entanglement, at what point do they happen? Will they happen, let us say we define point 1 entry, point 2 where the air is likely to meet, point 3 exit, point 4 outside the jet. Where do you think the opening of the filament would take place? The filament is coming from one side, between 1 to 2 opening, or between 2 and 3, or between 3 and 4, where? These questions are there. A lot of people obviously were looking at designs, turbulences, velocities being high and all change of design. This understanding is important. Where all these things happen? It is quite possible we can easily accept it that loop formation will not take place before opening. An entanglement obviously will not take place before loop formation. If this kind of thing happen, then obviously we do not know what kind of material we produce. So, although the exact timing may not be same for every filament, but overall we can approximately assume that opening of loops, opening of the filaments should proceed before loop formation, and entanglement must happen after loop formation. So, let us say if somebody asks this question, so where exactly the opening of the filament takes place, where exactly the loop formation takes place, and entanglement. So, these are some of the zones that we have described. Where do you think it will form? Between 1 to 2 opening? Possibly no, because entanglement opening can take place only when there is interaction. So, maybe between 2 3. The loop formation could be also similar. What is your opinion? Can everything happen somewhere else? What actually happens is, interestingly, outside the jet, it was noticed by various kinds of things that the whole thing is happening outside the jet. So, what was this fuss about more interaction, more turbulence, so that lot of things happen? This is quite surprising. Then why this all design business, converging, diverging, asymmetry and everything else? Majority of the filaments opened up at the exit. Why? Why do you think so should happen? Why can't they entangle while they are still in the inside the jet in the channel? Because for opening there has to be some force which is at an angle different to the motion of the yarn or the filament. If yarn is moving like this, and if all the forces are working in this direction, why would any filament separate? Why should it separate? It can only separate if there is some force which is acting in the direction which is different than the direction of motion of the yarn. So, as the yarn is coming, a filament bundle, it may be fluttering because of some velocity being high, some turbulence inside, but there is no real reason for it us to assume that would happen inside. Why would it happen outside? Here there is more pressure. As it comes out, what happens? Pressure will decrease or increase? As the air, compressed air is coming through a nozzle out into the open, the pressure would decrease or not? Yes, the pressure would decrease. Because the air can now go not just in front, but also in any other direction. By this, it means that you actually have some force which is taking the yarn in this direction, and there is some force acting just in the direction which is maybe at right angles. Now, this type of a force, if it is available, then there is a reason for us to believe that the filaments can open. One filament can go like this, the other filament can go like that, the other can go based on the resultant force that they experience at the exit. So, exit. Why it could happen? Because there was not much space, the pressure was very high, If the pressure is high, it is acting upon each filament. It does not say that go somewhere. So, it is compressing actually. So, it may go like this, the filament may not go straight like this, but it may flutter and go. But as it exits, suddenly there is a pressure drop, and because there is a pressure drop, the molecules of air are going in direction which is not necessarily the direction in which they immediately exit. So, there is another force with another direction, and that is the reason why filaments will start opening. So, when do they form the loop? So, loop formation, how does it happen? Why does it happen actually? Why would any filament make a loop? Obviously, we can now say with little more confidence that it will happen outside the jet. Where some filaments are moving like this, some filaments are moving like this, some are like that, and so they are now open. Why will the loop form? Loop would form only if one end is moving, the other end is not moving. If we create a situation that this does not move and the yarn is being pushed in this direction, so it will start bending, and that is how it will make loop. So, how does it stop? So, we have what we call as take up roll. These filaments, whatever they want, they cannot go without interacting at this point or somewhere. All of them have to come like this. All of them must converge at this point. So, how will they converge? So, this will probably make like this, this may make and then start entanglement here, this may do like this may make like that, the other one may do things like this. So, loop formation will take place, because we hope that this, which is a take up roll, is moving slowly. Slowly means what? It can't be slower than the feed roll. It is fast, or is it slow? It is slow, because you are giving overfeed. So, what is happening? So, you are giving overfeed, this anyway moving slow, but the filaments may be moving faster because of the overfeed, and therefore, one end is moving slowly, the other end is moving fast, and you make a loop, and then something like this happens. So, it is also happening outside, but individual filaments are bending. Now, the question that comes, all of them have been given overfeed simultaneously. If all of them go differently, but finally converge, make loops, why would they entangle? That means they just bent. So, they just come out of the take up roll and then they open again. If they open, it is all useless, the whole work is useless. To ensure that it is not useless, but useful, that means entanglement must take place. Now, this question again comes, why does the entanglement take place? If all the filaments make loops, because they had no overfeed, they were moving faster than the take up roll, so they make loop together. So, they are happy making loops, but why entanglement? You must understand, let us say the yarn is moving some average speed at about 350 meters per minute, let us say, at the take up. and we do understand, just because the loop has been formed, the average speed of the individual filament must be higher than this, then the loop will form, there is a pressure out there. And we can also assume that the average speed of the air at the exit will be more than the speed of the filament, because there is a slip also. The air is not gripping the filament like a roller, right. It is moving fast, and so it is taking the filaments along with it, but we can assume that the speed of the individual filaments would be higher than this, and the speed of the air, average speed of the air, should be higher than that of the filament. Can there be any confusion in this? What if somebody asks, if the yarn is being texturized or is being taken up by a roll at about 350 meters, what is likely to be the average speed of the air at the exit? Any guesses? 500, 600, 1000, what? Interestingly, the air actually is moving at a supersonic speed, and what is supersonic? Obviously, it may be close to 400 meters per second, not minute. So, this converging of a jet creates this high velocity, supersonic, and so you would have a lot of drag. Filaments going to be pulled through the jet. Of course, they are open, but let us say somebody again asks this question, what would be the average speed of an individual filament? More than 350 definitely, 350 meters per minute. Will it be close to 400 meters per second? May not be, because it is going to be slipping, it is not a full grip. But interestingly, the speed, average speed of the filaments could be 10 times higher than take up speed. If this is 350, the filament may be doing 3500 meters per minute. What a speed! And all this is happening in very short period of time. You already understood how much less time is spent inside the jet, although now we know almost everything is happening outside jet, but jet is important, creating high velocity. And also opening. Now, you can probably appreciate why they are diverging. Why can't they just have this thing, a straight cut, non-divergent exit? So, if it is straight, non-divergent, the pressure drop will be immediate. The filament may be flying all over. So, you can control. If you have the exit little controlled, then it will, pressure will drop, but at a rate at which you want. So, a lot of work was done also on what could be the angle and the length of this exit, which is a conical, diverging, but without much difficulty, it will be easy to, it is easy to understand that this expansion will be controlled. That is one. Converging of the jet, we understand will increase the velocity. So, more drag will be there and filaments are going to move at a faster pace. Now, because the difference is there between the take up velocities or speed and that of the filament average speed, loop formation takes place. So, these two things have been explained. Why entanglement? This is just good enough to open the filaments and move them faster. If entanglement has to take place, the speed of different filaments at any given point of time must not be same. If they are same, then opening will take place together, of course, and loop formation will also take place together. Entanglement will not take place. So, if somebody says what would be the profile of the air velocity, if it was low velocity situation like a Newtonian flow through any tube, the profile would be like this. The fluid which is moving and is close to the walls will move slowly. The ones which is the center will move faster. True. That means, if the filament happens to be, let us say, near the wall, it may be moving slowly. Okay. But because of turbulent velocity situation, the profile which has been measured is at the exit, something like that. At the center, it is not necessarily the highest velocity, because of the molecules in turbulence, they may be hitting each other in the center more. Of course, they will hit everything else also. So, maybe part of it is true that near the wall this velocity will be the lowest. Somewhere you have in the center velocity higher, but not exactly the highest. At the two halves there will be velocity which may be higher, but this is a good thing for us. Why is it good thing? Because now filaments will be moving out based on their position in the jet, whether they are here, 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 or any other way. Based on their position, they will be moving out at different velocities. Now, why is it important to us? It is important because the overfeed which we are giving is constant, same for each filament. But if the velocity are different, velocities, speeds are different, then this overfeed will be consumed first by such filaments which are moving faster, and they will form the loop. And after, because they were wherever they were, and the moment they make a loop, the tension in the filament will increase. So, this filament will try to come to the center of the jet exit, because now tense. When it is free, it moves along with the direction of the flow of air. But when the loop has been formed, because whatever overfeed was there for that particular filament has been consumed because it is moved, is made a loop. The tailing portion will, if it was, let us say, at this point, because it is consumed, it will push itself down almost to the center. So, this filament is moved down. Other filament which has still not consumed its overfeed, obviously under much less tension, it will flow the air direction of the air flow and maybe move out. So, some filaments which consume their overfeed at given point time. There are some other which have not consumed because they were moving at a slower speed, and so they would start moving out. The one which is consumed completely, the overfeed will start coming in the center. So, this thing will happen which we call as a migration. So, tension in the filament will vary because at different point of time, different filaments would be consuming their part of the overfeed, and so after consuming the overfeed they would become tense, and so they will migrate. The moment you migrate, entanglement starts happening. So, this filament, let us say, is moving faster, has made the loop. This filament was moving slowly, is still there. This will like to come down, this is still going up, but maybe at a point of time it will make a loop somewhere there, and similarly, and so they will move up, they will go down as the loops formation takes place. And so, it is quite possible at some stage this is actually moving like this, the other one is going up, and so they are moving and migrating, and because they are moving and migrating, therefore, you will have entanglement. Some will go to the surface, some will be in the core, the one after some time in the core will move out, the one which is in the surface will move in, and so loops also will thus be formed, where one filament is like this, the other one went like that, this one goes down, and so you will get loops of various types being formed. And everything is happening here because all of them finally must make a loop and then go from here, make a loop, and then with the loop go out of this take-up roller. Is this clear? Outside the jet, the pressure drops, so filaments separate. Filaments are moving at a very high speed compared to the take-up roller, and therefore, they make loops. Filaments are not moving at the same speed, and therefore, migration will take place, and therefore, entanglement will take place. Remember now, all the three important things are happening outside the jet. So, as the designs were being discussed, people wanted to know, is it necessary that the yarn which is coming out at the exit passes through a take-up roll which is aligned with the center of this nozzle. This is what is being done, the loops still form, entanglements may still happen because there is this one is moving slowly. But suppose we change this and make a simple change and say that this is not in a line, but it is actually almost at right angles to the path of the yarn motion. What happens? This one goes like this, but still has to come back. Some migration may take place, this one goes like this and has to come back. This one goes up and has to come back. And obviously, remember this happening in 3 dimensions. It is not that in 2 dimensions it is saying either here or there. The loop can form whichever way it forms. But the more important thing is, the moment you change the direction, something wants to move in this direction, suddenly pull it down, the tension here will be more. Remember, we just discussed somewhere, if the tension is higher, entanglements will be tighter. And they could find that if you have the take up at right angles to the nozzle, the withdrawal is at right angle to the nozzle axis, then you just produce yarns which are of better quality, and there is hardly any cost. Yarn does not mind you take up from whichever direction you want to take. Make sense? Simple innovation. So, this is how one can think of. Let me see if we can do something. Okay. So, if we are moving parallel to the nozzle axis, withdrawing, and if you look at the cross section of a jet, then you find that all the filaments have a equal probability of being found in the cross section of the jet without any bias. Of course, they will be changing their positions and they will be migrating, but at any given point of time you see, well, there are every part of the thing is approximately filled up with some filament or the other, right. But if you do at right angles, so there will be a bias, more filaments will be, if you are withdrawing in this direction, will be at this point, some of course will be here and one or two may be there as well, based on what has happened to them, but majority will fall in this region. So, they are, because you are pulling in that one direction. So, in the same direction more filaments will be there, because everything is being pulled down. So, migration will still take place, because they have to first cross and then come, if we are moving in this direction. Is that clear? So, if one uses a baffle plate at the end of the exit, a freely hanging, let us say a baffle plate, what happens? Of course, the yarn is being withdrawn at right angle. Now, if we understand, it will strike, everything that is there will strike and has to come down, can't go further. It must strike because a hard rigid body. So, whatever moves goes out, all this is happening and then it angles. So, it helps to bend the filaments, instead of, in general, earlier the filament was first flying to whichever length and then come back. Now, it is going to be controlled. So, this plate will, filaments will strike the plate and then bend. So, because you have changed the direction and also now you have a control. So, if you do this control, then it works better. Loop frequency will increase, loop size could be reduced. So, you have higher bulk, more entanglement, and regular loop size is always good. You got to have lot of variation in loop size is not such a good idea in any case. At Tusslin 20, instead of using a plate at the exit, they had a bar which is, so the air can, the one which is excess air is not really doing much, the filament can go strike and obviously is being pulled down. So, it will come down, this one goes, it works out. So, obviously, based on the size, look, however, the air will keep moving in this direction or in this direction without any obstruction, unlike the one, air would be finding it difficult to move in up in this direction, it has to follow this path. So, this additional advantage you can say is aware. So, that is one of the type 20, for example, had this kind of a baffle bar. This type of a jet was type 14, everything else remaining same, converging, diverging, asymmetric entry of the air, right angle withdrawal and a plate. What more? After all this research of having too many pieces, something which is at the exit that could be changed, the feed tube could go in and out, so that velocities could be changed, the volume of chamber could be decreased or increased. Finally, some said that all this is not required, where you are having everything, you are having outside the jet. So, why are you doing such a complex design? So, the concept of single core jet, no different pieces. You say, how will it be advantage? One of the difficulty levels was in optimizing the parameter is that all these elements in the Tusslin could be adjusted, like the one who is an operator could adjust a bit, change the volume where the interaction is taking place of a chamber, and probably the properties could also be changed. But then depending upon who, whether this person is smart or not, a little change could make more differences. They said, why not have a jet where no change is required? So, what do? If yarns are different denier, you say, well, you define that if the denier range is this, use this jet, if denier range is this, use this type of jet, numbers, different numbers. So, the operator does not have to do any manipulation. If operator does not have to do any manipulation, then obviously it is a good idea, no change will take place as long as the jet is same, one parameter has just been taken care of. And if everything has to take place outside the jet, then why do all the fuss? Interesting. With all this design research, this happened. So, one of the interesting jet which came into existence was called the Hema jet. So, a trumpet shaped exit. Air can pass not from one nozzle inside, but can go from 2 or 3. These need not be meeting at the same point, another one could be somewhere here also. So, single core, no converging, just parallel, increase in velocity by more pressures, more nozzles, higher denier, more nozzle, lesser denier, single nozzle, and expand in a trumpet shape. Why trumpet? Why this kind of a shape instead of the other one? It is again controlling the decrease in pressure, but no serious reasons available except, well, the other conical thing were all patented, all angles. So, you got to have something else. But definitely if you change the shape, the length, the angle of this trumpet, things are going to obviously be different. But importantly, this became very popular, because now you had pressure control systems, nozzles could be going 1, 2, 3 different angles, could actually also have a possibility of giving twist or swirling motion also, if it helped in any manner. So, yarn could be fed from here, a multi-filament yarn, the air will go from here to here, the chances of this going backwards is very less, because the angles are pointing in the direction of the exit. It will also open the loops, and then at the end, for example, if you have a sphere or a blob in front and the take up is here, the filament will strike and come to this take up position. and like the other baffle bar, other air can go from all sides, right. Instead of a bar, you have a blob or a sphere in front of it. So, some change in designs we last. So, what have we learned? We have learned the mechanism of bulb development, air jet texturing, how all the three phenomena happen, the jet design features and importance of converging, diverging, asymmetric flow, withdrawal at right angles, role of baffle plate or a baffle bar, and single core jets. Wetting, we have understood and its role. So, how these design features have helped in reducing the instability and also consumption of air, as we earlier mentioned that compressed air is not cheap. You do need to spend money and energy to compress the air. So, the modern jets, as we know now, have higher speeds with which you can process them. At the same time, consumption of air also is reduced, because you could create higher turbulence, higher velocity by changing the jet exit or entry of the air. We stop here, meet next time. Thank you.